Welcome to our gentle journey along the world's longest river system, where the waters of the Nile complex flow northward for 6,650 kilometers, or 4,130 miles, through the heart of northeastern Africa, carrying the patient rhythm of seasonal floods and the accumulated sediments of ancient highlands toward the Mediterranean Sea. As you settle into comfort this evening, allow your mind to drift slowly along these ancient waterways, where the Blue Nile and White Nile converge at Khartoum to form the main Nile River, creating a lifeline that has sustained civilizations for over 5,000 years through the predictable cycles of flood and recession that define life along this remarkable watercourse. The Nile Basin covers approximately 3.3 million square kilometers, or 1.3 million square miles, encompassing portions of 11 countries and draining nearly 1/10 of the African continent through a network of tributaries, lakes, and wetlands that collect rainfall from highlands extending from the Ethiopian plateau to the mountains of the moon in Uganda. I wonder where you might be listening from tonight, what part of our world you call home, and what time your clock shows as these words reach you across the digital streams. Perhaps you might share that peaceful information with us in the comments below, creating our own gentle map of listeners scattered like tributaries across the globe. And if you find that these river wanderings bring you the rest you seek, consider subscribing to join us on future explorations of Earth's most tranquil yet magnificent waterways. The White Nile begins its journey at the northern shore of Lake Victoria, the world's second largest freshwater lake by surface area, covering 68,800 square kilometers, or 26,600 square miles, at an elevation of 1,134 meters, or 3,720 feet above sea level. Lake Victoria receives its waters from numerous rivers flowing down from the surrounding highlands of Uganda, Kenya, and Tanzania, collecting rainfall from an area of approximately 184,000 square kilometers, or 71,000 square miles. The lake's maximum depth reaches 84 meters, or 276 feet, and its waters flow northward through a series of rapids and falls that have carved deep gorges through ancient crystalline rocks over millions of years. The White Nile exits Lake Victoria at Ripon Falls near Jinya, Uganda, beginning its 3,700 kilometer or 2,300 mile journey toward its confluence with the Blue Nile at Khartoum, Sudan. The river flows initially northward through Uganda as the Victoria Nile, dropping approximately 500 meters or 1,640 feet in elevation over the first 500 kilometers or 310 miles of its course. The most dramatic of these elevation changes occurs at Murchison Falls, where the entire flow of the Victoria Nile is compressed through a rocky gap, only 7 meters or 23 feet wide, before plunging 43 meters or 141 feet into the gorge below. thunderous roar of these falls can be heard for several kilometers. Yet the falls represent only one brief moment of drama in the otherwise gentle progression of the White Nile toward the Mediterranean Sea, located more than 5,000 kilometers or 3,100 miles downstream. After passing through Murchison Falls, the Victoria Nile enters Lake Albert, a smaller lake covering 5,300 square kilometers or 2,050 square miles at an elevation of 619 meters or 2,030 feet above sea level. Lake Albert, known locally as Lake Mabutu, sits within the western branch of the Great Rift Valley, its elongated shape reflecting the tectonic forces that created this remarkable geographical feature. The lake reaches maximum depths of 51 meters or 167 feet and serves as a natural reservoir that moderates the flow of the White Nile, storing excess water during periods of high rainfall and releasing it gradually during drier seasons. Exiting Lake Albert as the Albert Nile, the river flows northward through South Sudan and enters the vast wetland region known as the Sud, one of the world's largest freshwater wetlands, covering approximately 57,000 square kilometers or 22,000 square miles during the flood season. The Sud represents a remarkable geographical feature where the White Nile loses approximately half of its flow to evaporation and transpiration. As the river spreads across an almost perfectly flat landscape with gradients of less than 5 centimeters per kilometer or 3 inches per mile. The name Sud derives from the Arabic word for barrier, reflecting the dense vegetation that historically made navigation through this region extremely difficult for early explorers. Within the Sud, the White Nile divides into numerous channels that meander through floating islands of papyrus and other aquatic vegetation, creating a maze of waterways that shift positions seasonally as water levels rise and fall. During the dry season, the main channel may narrow to widths of only 100 to 200 meters or 330 to 660 feet, while during floods, the waters may spread across areas 50 kilometers or 31 miles wide. The floating vegetation islands, known locally as Sud blocks, can break free during high water and drift downstream, sometimes blocking navigation channels and altering the river's course. These vegetation mats may be several meters thick and support their own ecosystems of plants, insects, birds, and small mammals as we follow the White Nile's patient progress through these vast wetlands. Perhaps you might reflect on what draws you to such expansive water landscapes. What aspects of rivers and marshlands bring you a sense of peace and tranquility? If you feel moved to share such thoughts in the comments below, many would find comfort in reading about the watery places that soothe our restless minds. The White Nile emerges from the Sud near Malakal, South Sudan, having lost approximately 14 billion cubic meters, or 11.3 million acre-feet of water annually to evaporation and plant transpiration within the wetlands. From Malakal, the river continues northward through increasingly arid landscapes, receiving only minimal additional flow from seasonal tributaries as it approaches its confluence with the Blue Nile at Khartoum. The White Nile's contribution to the combined flow at Khartoum averages approximately 26 billion cubic meters, or 21 million acre-feet annually, representing about 16% of the total Nile flow during most years. Though this proportion increases significantly during dry years when Blue Nile flows diminish. The Blue Nile begins its journey at Lake Tana in the Ethiopian highlands, situated at an elevation of 1,788 meters, or 5,866 feet above sea level. Lake Tana covers approximately 3,200 square kilometers, or 1,200 square miles, and reaches maximum depths of 15 meters, or 49 feet, making it the largest lake in Ethiopia and the source of approximately 85% of the Nile's flow during the flood season. The lake receives water from more than 60 tributaries flowing down from the surrounding highlands, where annual rainfall exceeds 2,000 millimeters, or 79 inches in some areas, contrasting dramatically with the desert regions downstream, where annual precipitation may be less than 25 millimeters, or 1 inch. The Blue Nile exits Lake Tana as the Abe River and flows southeastward for approximately 30 kilometers, or 19 miles, before turning northwestward and beginning its descent through a series of spectacular gorges carved through the Ethiopian plateau. The river drops more than 1,400 meters, or 4,590 feet in elevation over the first 800 kilometers, or 500 miles of its course, creating numerous waterfalls and rapids, including the Blue Nile Falls, known locally as Tees Bay, or Smoking Water, where the river plunges 45 meters, or 148 feet, over a basalt cliff during the rainy season. Blue Nile Gorge, carved through layers of volcanic rock over millions of years, reaches depths exceeding 1,500 meters, or 4,920 feet below the surrounding plateau surface, creating one of the most dramatic river canyons in Africa. The gorge extends for approximately 800 kilometers, or 500 miles, through the Ethiopian highlands. Its steep walls, exposing geological formations that record millions of years of volcanic activity and erosion. The river's gradient through the gorge averages approximately 2 meters per kilometer, or 10 feet per mile, creating numerous rapids and cataracts that have historically prevented navigation of this section of the river. During the rainy season from June through September, the Blue Nile's flow increases dramatically as monsoon rains drench the Ethiopian highlands, transforming streams into torrents that carry vast quantities of sediment toward the main river. The Blue Nile's peak flows may exceed 8,000 cubic meters per second, or 282,000 cubic feet per second during flood conditions, compared to dry season flows that may drop below 300 cubic meters per second, or 10,600 cubic feet per second. This enormous seasonal variation, with a ratio exceeding 25:1 between maximum and minimum flows, has shaped the rhythm of life along the Nile for thousands of years. The Blue Nile crosses from Ethiopia into Sudan near the town of Assosa, continuing northwestward across the gradually sloping plains toward its confluence with the White Nile. The river's gradient decreases significantly once it leaves the Ethiopian highlands, dropping only 300 meters or 980 feet over the remaining 800 kilometers or 500 miles to Khartoum. This gentler gradient allows the river to deposit much of its sediment load across the fertile plains of eastern Sudan, creating some of the most productive agricultural soils in the region. The confluence of the Blue and White Niles at Khartoum, the capital of Sudan, creates one of the most remarkable geographical sites in Africa, where the clear waters of the White Nile meet the sediment-laden brown waters of the Blue Nile. The two rivers flow side by side for several kilometers downstream from their confluence, their different colors and densities preventing immediate mixing. The combined flow continues northward as the main Nile River, carrying an average annual discharge of approximately 84 billion cubic meters, or 68 million acre-feet toward the Mediterranean Sea. The main Nile flows northward from Khartoum through increasingly arid landscapes, traversing the Nubian Desert, where annual rainfall drops to less than 5 millimeters or 0.2 inches per year in some areas. The river receives virtually no additional flow from tributaries along this 2,700 kilometer or 1,680 mile section to the Mediterranean coast, losing water primarily through evaporation from its surface and through infiltration into the surrounding desert sands. The river's course through Sudan and Egypt has been significantly modified by human intervention, including the construction of numerous dams and reservoirs that regulate flow and provide irrigation water for agricultural development. The Nile's passage through the Nubian Desert includes 6 major cataracts, rocky barriers created by resistant geological formations that create rapids and falls in the river channel. These cataracts historically served as natural boundaries between different kingdoms and empires, with the first cataract near Aswan marking the traditional southern boundary of ancient Egypt. The cataracts range in length from a few hundred meters to several kilometers and create elevation drops ranging from 5 to 50 meters or 16 to 164 feet, requiring extensive engineering works to allow modern navigation and water control. Perhaps you have experienced peaceful moments near rivers or large bodies of water that brought you feelings similar to those we explore along this ancient watercourse. If you feel inclined to share such experiences in the comments, others would find comfort in reading about the aquatic places that have provided you with tranquil reflection. The Aswan High Dam, completed in 1970, represents one of the most significant modifications to the natural Nile system, creating Lake Nasser, a reservoir extending 550 kilometers or 340 miles upstream from the dam, and covering approximately 5,250 square kilometers or 2,030 square miles at full capacity. The reservoir can store up to 162 billion cubic meters or 131 million acre-feet of water, nearly twice the Nile's average annual flow, allowing complete regulation of river discharge and elimination of the natural flood cycles that had characterized the river for thousands of years. The dam rises 111 meters, or 364 feet above the riverbed, and extends 3,830 meters, or 12,570 feet across the Nile Valley, creating a massive barrier that has fundamentally altered the river's ecology and the lives of millions of people downstream. North of Aswan, the Nile flows through the narrow valley carved through the Egyptian desert, where the river's floodplain rarely exceeds 20 kilometers or 12 miles in width, and often narrows to less than 3 kilometers or 2 miles between the encroaching desert cliffs. This narrow ribbon of fertility, irrigated by Nile water for over 5,000 years, supports a population density exceeding 1,500 people per square kilometer, or 3,900 people per square mile in some areas, making it one of the most intensively cultivated regions on Earth. The contrast between the lush green of the irrigated fields and the barren brown of the surrounding desert creates one of the most striking landscape transitions visible from space. The Nile Delta begins approximately 165 kilometers, or 103 miles north of Cairo, where the river divides into multiple distributary channels that spread across the coastal plain toward the Mediterranean Sea. The delta covers approximately 24,000 square kilometers, or 9,300 square miles, an area roughly equivalent to the size of Vermont, or half the size of Switzerland. The delta's triangular shape, which gave this landform its name derived from the Greek letter delta, extends approximately 240 kilometers, or 150 miles from east to west along the Mediterranean coast, and penetrates approximately 160 kilometers, or 100 miles inland from the coastline. The Nile Delta represents one of the world's most productive agricultural regions, with fertile soils built from thousands of years of sediment deposition during annual floods. Before the construction of modern dams, the Nile deposited approximately 124 million tons of sediment annually across the delta, gradually extending the coastline into the Mediterranean Sea and building new land at rates of several meters per century. The elimination of natural flooding by dam construction has significantly reduced sediment delivery to the delta, leading to coastal erosion in some areas and requiring increased use of artificial fertilizers to maintain agricultural productivity. Currently, the Nile reaches the Mediterranean through two main distributary channels: the Rosetta branch on the western side of the delta and the Damietta branch on the eastern side. Historical accounts describe as many as 7 major distributary channels operating during ancient times. But human modifications and natural processes have reduced this number while concentrating flow through the remaining channels. The combined discharge of these channels averages approximately 30 billion cubic meters, or 24 million acre-feet annually. Though this flow is heavily regulated by upstream dams and irrigation diversions, the Mediterranean coastline of the Nile Delta extends for approximately 240 kilometers, or 150 miles, characterized by low sandy beaches, coastal lagoons, and salt marshes that provide habitat for numerous migratory bird species. The coastal zone experiences a Mediterranean climate with mild, wet winters and hot, dry summers, receiving between 100 and 200 millimeters, or 4 to 8 inches of annual precipitation. Sea level variations in the eastern Mediterranean are minimal, typically ranging less than 30 centimeters or 12 inches annually, allowing the development of stable coastal ecosystems and human settlements. The seasonal flooding that historically characterized the Nile system followed predictable patterns linked to the monsoon rains over the Ethiopian highlands. Flood waters typically began arriving in Egypt in late June or early July, reaching peak levels in September before gradually receding through November and December. The flood season, known in ancient Egypt as Akhit, deposited fertile silt across the floodplain, while the recession period, called Perit, provided ideal conditions for planting crops in the moist, enriched soils. The harvest season, Shemu, occurred during the hot, dry months before the arrival of the next flood cycle. These flood cycles carried an average of 110 million tons of sediment annually past Cairo before dam construction, with concentrations reaching 2 to 4 grams per liter, or 0.27 to 0.53 ounces per gallon during peak flood conditions. The sediment consisted primarily of clay and silt particles eroded from the volcanic soils of the Ethiopian highlands, creating some of the most fertile agricultural soils in the world when deposited across the Nile's floodplain. The predictability of these floods allowed the development of sophisticated agricultural systems and contributed to the stability of ancient Egyptian civilization for over 3,000 years. The Nile's role in ancient Egyptian civilization extended far beyond agriculture, providing transportation routes, construction materials, and religious significance that shaped virtually every aspect of life along the river. The river's north-flowing current allowed easy downstream transport of goods and people, while the prevailing northerly winds facilitated upstream travel under sail, creating a natural transportation system that connected the Mediterranean coast with the heart of Africa. Papyrus growing in the Nile's marshes provided raw material for the world's first paper, while the annual floods deposited not only fertile soil, but also the clay necessary for brickmaking and pottery. The religious significance of the Nile in ancient Egyptian culture reflected the river's central role in sustaining life in an otherwise arid landscape, with numerous deities associated with different aspects of the river's annual cycle. Hapi, the god of the Nile flood, was depicted as a hermaphroditic figure, symbolizing the river's life-giving properties, while Sobek, the crocodile god, represented the Nile's power and danger. The river was viewed as a pathway between the world of the living and the afterlife, with the daily journey of the sun god Ra across the sky, paralleling the north-flowing current that carried the dead toward their eternal rest. Modern management of the Nile system involves complex international agreements and engineering projects that attempt to balance the water needs of 11 different countries while maintaining adequate flows for navigation, agriculture, and urban water supplies. The Nile Basin Initiative, established in 1999, provides a framework for cooperative development of the river's water resources. Though disagreements over water allocation continue to create tensions between upstream and downstream countries, Ethiopia's construction of the Grand Ethiopian Renaissance Dam on the Blue Nile represents the most significant new development affecting the system, with a planned storage capacity of 74 billion cubic meters, or 60 million acre-feet, that will provide flood control and hydroelectric generation, while potentially altering downstream flow patterns. The ecological diversity supported by the Nile system includes hundreds of fish species, numerous migratory bird populations, and remnant populations of large mammals, including hippopotamuses and crocodiles. The Sud wetlands alone support more than 400 bird species and provide critical habitat for the world's second largest wildlife migration, involving approximately 1.3 million white-eared kob and other antelope species. Lake Victoria contains more than 500 species of cichlid fish, most found nowhere else on Earth, representing one of the most remarkable examples of rapid evolutionary diversification in freshwater environments. The water quality of the Nile varies significantly along its course, from the relatively clean waters of Lake Victoria and the Ethiopian highlands to the increasingly polluted waters of the lower river, affected by agricultural runoff, industrial discharge, and urban sewage. Nutrient levels increase dramatically downstream from major cities, creating eutrophication problems in some reaches and affecting aquatic ecosystems adapted to the historically clean waters of the natural river system. Pollution control efforts face significant challenges given the large human populations dependent on the river and the varying environmental standards among the 11 countries sharing the watershed. Climate change projections suggest significant potential impacts on Nile flow patterns, with most models predicting reduced precipitation over the Ethiopian highlands and increased evaporation rates throughout the basin. Temperature increases of 2 to 4 degrees Celsius, or 3.6 to 7.2 degrees Fahrenheit, projected for the region by 2100, could increase evaporation rates by 10 to 20%, while changes in monsoon patterns might alter the timing and magnitude of Blue Nile floods. These changes could affect the 400 million people currently living within the Nile basin and dependent on the river for water, food security, and economic development. As our journey along this ancient river system approaches its conclusion, perhaps you might reflect on which elements of these flowing waters and river landscapes you find most conducive to peaceful relaxation. If you feel moved to share such observations in the comments below, many listeners find that reading about what brings others peaceful sleep helps enhance their own rest. The Nile's connection to human civilization spans more than 5,000 years of recorded history, during which the river has remained a constant presence while empires rose and fell along its banks. The predictable rhythms of flood and recession that sustained ancient civilizations continue today in modified form, with modern dams and irrigation systems replacing natural processes while maintaining the fundamental relationship between the river and human survival in this arid region. The accumulated wisdom of countless generations of farmers, engineers, and water managers represents a remarkable record of human adaptation to riverine environments. The geological processes that created the Nile basin operate on timescales spanning millions of years, from the tectonic forces that elevated the Ethiopian highlands and created the Great Rift Valley to the gradual erosion that carved the river's channel through ancient rocks and deposited fertile sediments across the delta. The current configuration of the Nile system represents only the most recent chapter in a geological story that began with the breakup of the supercontinent Gondwana and will continue as long as rainfall falls on the African highlands and gravity pulls water toward the sea. The hydrological cycle that drives the Nile system connects local weather patterns in East Africa with global atmospheric circulation. As moisture evaporated from the Indian Ocean falls as rain on the Ethiopian highlands before beginning its journey toward the Mediterranean Sea. This connection demonstrates the fundamental unity of Earth's water cycle, where every drop of water participates in an endless circulation between ocean, atmosphere, and land that has operated for billions of years and connects the Nile with every other river, lake, and ocean on our planet. The mathematical precision of the Nile's flood cycles, recognized and utilized by ancient Egyptian astronomers and modern hydrologists alike, reflects the orderly operation of physical laws governing the movement of water across continents and through watersheds. the relationship between rainfall patterns thousands of kilometers upstream and flood heights at Cairo demonstrates the interconnected nature of continental-scale hydrological systems, where local changes can have effects that propagate across entire river basins over periods of weeks to months. The sedimentary record preserved in Nile Delta deposits and lake sediments throughout the basin provides a detailed archive of climate changes, volcanic eruptions, and human activities spanning thousands of years. These sediments contain pollen grains that record vegetation changes, mineral particles that indicate source rock erosion, and chemical signatures that reflect precipitation patterns and temperature variations. The study of these sedimentary archives reveals that the Nile's flow has varied significantly over geological time, with periods of enhanced flow during ice ages alternating with reduced flows during warm periods. The Nile's role as a corridor for human migration and cultural exchange has connected Mediterranean civilizations with the heart of Africa for thousands of years, facilitating the movement of people, ideas, technologies, and trade goods across one of the world's most challenging geographical barriers. The river provided the only reliable route through the Sahara Desert, allowing the development of trade networks that connected the gold mines of Nubia with the markets of the ancient world, and facilitating cultural exchanges that influenced the development of both African and Mediterranean civilizations. As we reach the end of our mental voyage along this timeless watercourse, we return to the eternal cycle of evaporation and precipitation, of rainfall in distant highlands and gradual flow toward the sea, that has sustained life along the Nile for millions of years and will continue long after current human civilizations have passed into history. The river flows with the same patient persistence that characterized its journey when dinosaurs roamed the earth, carrying water from mountain springs to ocean depths through landscapes that change constantly, yet maintain their essential character across geological ages. The gentle murmur of flowing water continues day and night along thousands of kilometers of the Nile's course, a sound as constant as breathing, as persistent as the heartbeat of the earth itself. The temperature of the water varies only gradually along the river's length, warming slowly as it flows from the cool highlands toward the warm coastal plains, creating stable aquatic environments that support continuous biological activity throughout the year. The clarity of the water reflects the cleanliness of its mountain sources, allowing sunlight to penetrate to considerable depths and supporting the photosynthetic processes that form the foundation of riverine food webs. In this realm, where water moves with gravity's inexorable pull toward the sea, where annual floods have repeated their cycles for millennia, and where the horizon extends across vast wetlands and fertile plains toward distant mountains, we find a landscape that invites contemplation of continuity and renewal beyond human timescales. The water molecules that flow past any point on the river participate in journeys that began with evaporation from the Mediterranean Sea, continued through atmospheric circulation and highland precipitation, and will end with return to the sea, where the cycle begins anew. As consciousness fades into the peaceful realm of sleep, imagine yourself sitting quietly beside the slow-moving waters of the White Nile in the early evening light, watching the gentle current carry water hyacinth and papyrus downstream, while listening to the soft calls of water birds settling into their nighttime roosts among the reeds, feeling the warm breeze that carries the scent of river water and growing vegetation across the vast floodplain that stretches toward the horizon. The river flows past with infinite patience, its surface reflecting the first stars appearing in the darkening sky, its steady murmur providing a constant rhythm that connects this moment with countless others throughout history, when humans have found peace beside flowing water. And if this journey along the ancient Nile has brought you closer to the peaceful sleep you seek, remember to subscribe to join us on future explorations of our planet's most magnificent yet soothing waterways, where the patient flow of rivers toward the sea invites rest and renewal far from the urgency of modern concerns.